Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself again. My name is Pramudito Bagas Umboro. I am from the class of Numerical Methods 01. In this series, this will be the second series. In this series, I will be explaining the practical applications of die 5 in problem. So we have a problem to determine the pressure drop in a pipe system with fluid flow using computational fluid dynamics. In applying die 5 to solve the problem, first we apply the first step, I'm my consciousness, which means we have to be fully conscious. Now, first we must be aware and recognize the importance of understanding fluid dynamics in engineering applications, such as piping systems in HVAC, water supply, or chemical processes. And we must concentrate on understanding the parameters that affect pressure drop, such as fluid properties, pipe geometry, and flow rate. And then our intention. Our goal is to accurately calculate the pressure drop across the pipe system using CFD to optimize the design and ensure efficient operation. Purpose is to help in reducing energy consumption and preventing potential failures in the system due to incorrect pressure predictions, as well as my intention to apply my knowledge gifted by Allah Subhanahu wa Ta'ala in this problem. So in my case, I will say Bismillah before starting. And then the third step is initial thinking. We must gather all necessary data, including the physical dimensions of the pipe, properties of the fluid, its viscosity and density, and so on, and boundary conditions, the inlet velocity and outlet pressure, and everything else. And then we must think about the basic principles of fluid dynamics that apply, such as Bernoulli's equation and Darcy-Weisbach equation for pressure drop. And then the fourth step is idealization. We develop a CFD model of the pipe system, define the geometry, mesh the domain appropriately, and set the boundary conditions. And then we must assume initial conditions and run preliminary simulations to get a rough estimate of the pressure drop. Using the simulation results to visualize the flow patterns, we identify any areas of turbulence or recirculation that might affect the pressure drop. And then the final step is instruction. When we run the CFD simulations, there will be varying parameters to understand their impact on pressure drop. And then we adjust the mesh and solver settings for higher accuracy. We then analyze the results, compare them with theoretical calculations and experimental data if available. And then we use the insights gained to optimize the pipe design, such as changing the pipe diameter, smoothing bends, or altering flow rates to achieve the desired pressure drop with minimal energy loss. And then we have a second problem. The next problem is, for example, we are trying to minimize travel time across a river. The problem is you are standing on the edge of a slow-moving river which is 1 mile wide and wish to return to your campground on the opposite side. You can swim at 2 miles per hour and walk at 3 miles per hour. The campground is 1 mile from the point directly across the river from where you start your swim. What route will take the least amount of time? Using the first step of die 5, I'm my consciousness, we must recognize the importance of minimizing travel time by considering both swimming and walking speeds. And then we must concentrate on understanding the distances and speeds involved in both swimming and walking. And then our intention, we must find the goal, we must find the optimal path that minimizes total travel time and ensure an efficient and quick return to the campground, as well as apply the knowledge gifted by God, Allah Subhanahu wa Ta'ala, and say Bismillah. And then initial thinking. We must understand that the distance across the river, which is 1 mile, the swimming speed, which is 2 miles per hour, walking speed 3 miles per hour, and the campground location, 1 mile from the point directly across the river. We must take all of that into consideration. And then we use the relationship between distance, speed, and time to set up the problem. And then, in idealization, we must develop a mathematical model to minimize time travel. Let x be the distance downstream where you land after swimming. And then we draw a diagram showing the swimmer's path and the walking path. And then in the last step, which is instruction, we must put into we must put the data into the equations to find out how long it will take to swim and walk to the campgrounds. For the time to swim, it will be equal to square root of 1 plus x squared divided by 2. And time to walk will be 1 minus x per 3. And the total time will be those two equations added. And so, in the optimization, we differentiate t with respect to x and set the derivative to 0 to find the minimum time. Solve for x to determine the optimal landing point. After solving the optimal distance downstream to land for the least travel time is x equals 0.6 miles. Total minimum time taken is approximately 0.83 hours. And then the next problem. We have 50 apple trees in an orchard, each producing 800 apples. For each additional tree planted, the output per tree drops by 10 apples. How many trees should be added to maximize the total output? In the first step, I my consciousness, we must be aware and understand the relationship between the number of trees and total apple production. And then we must concentrate on balancing the number of trees with the reduction in apple output per tree. Our intention is to maximize the total apple production in the orchard and ensure the highest possible yield from the orchard, as well as apply this knowledge gifted by God. Bismillah. And then we go to initial thinking. We must see the data that we are given, which is the initial number of trees. There are 50, and the apples produced by every tree is 800, and the decrease in apples per additional tree is 10. And we must set up an equation to represent total apple production. And then we have the fourth step, idealization. We let x be the number of additional trees planted. And so the total apples will be 50 plus x times 800 minus 10x. We will then plot the function to understand the relationship between x and total apples. And then the final step, instruction, we expand the function into y equals 50 plus x times 800 minus 10x into 40,000 plus 300x minus 10x squared. We expand the function into y equals 40,000 plus 300x minus 10x squared. And then we differentiate and set to 0 dy over dx equals 300 minus 20x equals 0. And then solve for x equals 15. And then we verify that x equals 15 gives a maximum by checking the second derivative or analyzing the graph. And so we come to the conclusion that we must add 15 trees to the orchard to achieve maximum apple production, yielding a total of 575 times 65 equals 37,375 apples. And then we go to the final problem that I have set for numerical methods. The problem will be car B is 30 miles directly east of car A and begins moving west at 90 miles per hour. At the same moment, car A begins moving north at 60 miles per hour. What is the minimum distance between the cars and at what time does it occur? Using the first step, I my consciousness, we must recognize the importance of relative motion between two moving objects. Concentrate on understanding the motion paths and their impact on distance. And our attention is to find the time at which the distance between the cars is minimized and ensure accurate calculation of the minimum distance, as well as applying our knowledge gifted by God. Bismillah. And then we go to initial thinking. We must understand and collect the data of the initial positions and speeds of both cars. And then we use the Pythagorean theorem to express the distance as a function of time. And then the fourth step, idealization, we must make a model. Let x be the distance car A travels north and y the distance car B travels west. And so we get a function of the function t equals square root of 60t squared plus 30 minus 90t squared. And then we plot the distance function over time to identify the minimum point. And then the final step is instruction. We calculate the distance function and expand it. We find function of t equals to 3600 t squared plus 30 minus 90t squared. Differentiate LT into dl per dt, which equals to 7200t minus 5400 divided by square root of 3600t squared plus 30 minus 90t squared. And then we set the derivative to 0 and solve for t 7200t minus 5400 equals 0. And so we get t equals 3/4 of an hour. And then we check that this value of t corresponds to a minimum of evaluating the second derivative or examining the graph. And so we get that the minimum distance between the cars occurs at t equals 3/4 of an hour, and the distance is approximately 24.96 miles. In conclusion, using the die-5 method, we systematically approached and solved each optimization problem. This structured approach helps in understanding the problem deeply, setting clear goals, gathering necessary data, conceptualizing solutions, and implementing them effectively. Thank you for watching. Please join me for the third series where I will be applying die-5 to a series of problems regarding or connected to fluid mechanics. I will see you then. Thank you for watching. Wassalamualaikum warahmatullahi wabarakatuh.